Let's have a quick show of hands. So who here is using JDK 8 in some way, shape or form? Good, good. We have the right audience there. So what I want to talk about this evening is, as the title would suggest, some of the things to do with performance when it comes to Lambda expressions and Streams API. And it's not really like just a simple, here's what you do to make your code perform well. It's more about looking at how some of these things work so that you can understand a bit more about what's going on underneath. So that when you write your code, you understand more about how to get performance out of what you're doing. So, I have divided it up into a number of sections. We'll start off with a little bit about Lambdas and how they work under the covers from a performance point of view. Then we'll talk about streams versus external iteration, so using explicit loops rather than using the Streams API, and which could be a better performing one, and how you can never know until you've actually tried with your own code. So we'll talk some about benchmarks there. I've got a few tips for better performing streams. Actually, some of that's more about how to not write badly performing streams rather than how to write particularly well performing streams. And then we'll delve into parallel streams because there's quite a lot of useful information there. There's quite a lot of things that people kind of don't necessarily misunderstand, but parallel streams can be something that people overuse, shall we say. And then we're going to summarise. Right, so we'll start off with Lambda expressions. And Lambda expressions, as you know, were introduced in JDK 8. And people made a sort of big thing about Lambda expressions. They were a big new feature in that version of Java. I've got to admit, I never really thought that was the big new feature. I thought streams was actually more important than Lambda expressions. Because if you think about it, Lambda expressions are only a simple way of doing what you can already do with anonymous inner classes. So you can think of a Lambda expression like this. So we're using the iterable interface on the collection here, and we're saying we're going to use the for-each method. For-each method takes a consumer as a parameter. Consumer's a functional interface, so it has a single abstract method which we can implement using a Lambda expression. So we say, okay, look, we're going to do just print out whatever the words are in our list. And we can also simplify that a bit further by using a method reference, which is really just a way of simplifying what we've said in the Lambda expression, so that we don't have to specify any parameters, because the method reference will figure that out for us. All we're doing is just calling one method. We could also rewrite that using an anonymous inner class, and clearly that's a bit more verbose. And we actually have to specify a lot more things, so we can say, okay, it's a new consumer of type string, and we're going to override the accept method, which is public and void. So we have to specify the full signature of the method, and then we say what we're going to do. But functionally, all of those three are equivalent. There's no difference between them in terms of what they actually do. It is exactly the same thing. So it's really just, from this point of view, about how you can make your code easier to understand and less verbose. So if we look at anonymous inner classes in a little bit more detail, funnily enough, as the name would suggest, we are dealing with classes. So the compiler is looking at what you've said, and rather than you having to actually explicitly create a class with a name and a constructor and all the things that go with that class, the compiler generates a lot of that for you. So it will generate something like foo$1 as a class, and it will generate the code for that, and it will compile it. At that point, it's exactly the same as class. It is a class, so there's no difference from the point of view of how it's used. When the JVM uses that class, it has to load the class at runtime, and whenever you use the anonymous inner class as a parameter to another method, for example, it has to instantiate an instance of that class and use that object to do whatever it is you want to do. What that means is that we could, if we wanted to, implement Lambda expressions in exactly that way. We could simply take the Lambda expression or the method reference, we could convert it to the equivalent anonymous inner class, because every Lambda expression could be converted to an anonymous inner class, and we could then compile it. And if you look at the history of Lambda expressions, originally they were implemented that way. So they were just syntactic sugar on top of anonymous inner classes, and you didn't get any benefit from that in terms of performance. It was just about the syntax. To improve things, the developers of Lambdas had a look at that and they said, well, actually we can do better than that. So what we'll do is, rather than just converting it to an anonymous inner class, we'll use invoke dynamic. Now, invoke dynamic was the bytecode that was introduced in Java SE 7, and it was really intended primarily for improving the performance of dynamically typed languages that were being compiled into bytecodes and run on top of the JVM. And one of the big things that really held back the performance of these languages was method dispatch. So invoke dynamic was introduced as a way of allowing you to not have to have the exact types of the parameters and the return type of a method when you actually wanted to invoke it. So you could leave it to runtime rather than having to do it at compile time. You could wait until runtime so that the JVM would know the types of the parameters and the return type and could then figure out the signature of the method that you're actually using and invoke it dynamically. So that was really what it was designed to do. And what the developers of the Lambda expressions said was, well, that actually makes a lot of sense for doing Lambda expressions. What we want to be able to do is say, even though the types are all known, what we really want to do is to shift when we decide how to implement that method to runtime rather than doing it at compile time. If we do it at compile time, we're locking ourselves into a binary implementation. If we use invoke dynamic, we can then let the JVM make decisions at runtime and use different approaches based on what makes sense at that time. So when we do a compilation of a Lambda expression in JDK 8 now, what will happen is you will generate an invoke dynamic call, which is called the Lambda factory, wherever you use a Lambda expression. And what the invoke dynamic call does is it returns an instance of a functional interface type, which is the Lambda expression. The other thing that the compiler needs to do is to take the body of the Lambda expression and generate some method which is going to be used to implement that. So it will do something in terms of creating a method, but not necessarily if you're using a method reference. And this is one of those places where you immediately start to see where there can be some improvement in performance if you use a method reference. Because if you're using a method reference, then the compiler knows which method you're calling. There's no point in creating a method which contains a call to another method. You might just as well call the method that you're going to use, rather than wrapping it in another method. So that's one thing to be aware of. The other thing that's important about Lambda expressions is that they can be divided into two groups. One group is non-capturing Lambdas. This is where the Lambda expression that you're using doesn't reference any variables from the surrounding scope. So in that case, it's actually very simple for the compiler to deal with this. The compiler can actually generate a static method which you can insert into the class which is using the Lambda expression. And it simply passes the parameters of the Lambda expression and then generates the code which is going to be the method which actually executes the code you want it to do. So it's very simple from the compiler's point of view to implement that through a simple static method. Capturing Lambdas are ones that do reference variables from the surrounding scope. And so in this case, there are different strategies that the compiler can take in terms of how to deal with that. So one thing is it could do is it could actually do the same thing and create a static method which implements the body of the Lambda, but in addition to passing the parameters of the Lambda, it also passes the parameters which are the variables from the surrounding scope that it wants to use. So it can then reference them through the variables that are being passed. Or it could do it a different way, which is to create a synthetic method in the class so that it's actually using the instance of that class, which has the variables available to it. So you're just calling, in effect, a local method, rather than a static one. You're calling a local method in that object, and it can then reference those variables directly because it has access to them, because it's inside the object where those variables exist. And it's really up to the JVM to determine what makes most sense from a performance point of view to actually do the implementation at that point. Now, if you compare the implementation details, you can actually break down what's going on into 3 stages. And Oracle did some interesting analysis of the performance of these different stages to see what was working better, Lambdas or an anonymous inner class. And so the first bit is, in terms of the Lambdas, is linkage. And you can think of that as basically where the invoke dynamic gets used. In the case of the anonymous inner class, because it's a class, we need to load the class. Now at that point, if you look at the comparison in terms of performance, it varies. And what I mean by that is that if you are doing something where the code is on a hot path in terms of what's going on, then class loading will actually perform better than linkage through invoke dynamic, because invoke dynamic takes a while to warm up. The more call sites you have that are using Lambdas, the closer the performance will get. So you'll actually see a convergence in terms of performance between linkage and class loading based on how many call sites are actually being used. If, on the other hand, you're going through a cold path in the code, so it's not actually going through the JIT compilation, then you'll actually find that Lambdas will outperform, in terms of linkage, class loading by a factor of about 100. So that's interesting, but it won't help you one bit in terms of trying to decide what to do in terms of coding. I wouldn't recommend using anonymous inner classes because you suddenly think, oh wow, that's actually going to be on a particular code path, and so I'm going to get better performance from an anonymous inner class. Especially because we only talk about one part of what's going on. Now, the second bit is where we do the capture of the local variables and how we implement that. And as we've already seen, from the point of view of non-capturing Lambdas, these can be made static methods, and those can be inline very easily, and especially with method references, you get better method inline. Versus instantiation, which is obviously creating a new object, which has the overhead of allocating memory from the heap. You then have to initialize the object using the constructor and so on, and that's a lot more work. So the instantiation part is much less performant than capture of the Lambda zone. And then basically invocation of the method is exactly the same. So the third part is no different. What that really means is that from a performance point of view, Lambdas on the whole will outperform anonymous inner classes. There are some situations where you've got a hot path and you've got a small number of call sites, and Lambdas may give you slightly lower performance, but on the whole, you'll get better performance from Lambdas than you will from an anonymous inner class. So there's certainly no reason to think to yourself, right, I'm really, I need to get the last possible bit of performance out of my application. I'll change my Lambdas to anonymous inner classes because I think they'll work faster. Some things to remember in terms of your own code. Non-capturing Lambdas automatically optimize. So if you can, avoid Lambda expressions which do need to capture variables. Now, clearly that's something you can't avoid all the time. You need to have Lambda expressions sometimes where you do use variables from the surrounding scope, so that's just something that you can try. Method references are slightly more optimal because you don't have the extra overhead of another method call or a method call. So where you can, use method references rather than explicit Lambda expressions, because that will give you slightly better performance. And the other thing, if you look at the results of the analysis that Oracle did, was they compared tiered compilation versus non-tiered compilation, and they found that if you have tiered compilation switched on, then you get slightly better performance with Lambdas than you did with it turned off. Now, tiered compilation is on by default, so really what I'm saying is don't turn it off if you want better performance. Right, so that was Lambda expressions. Now let's talk about streams and external iteration. Common question that people ask is, which is better for performance? Streams with Lambdas or external iteration, explicit loops? Can we write an explicit loop that will actually be better in terms of performance than the equivalent stream? Unfortunately, the answer is most definitely not straightforward. Now, there have been a couple of articles that have been written recently which are trying to use benchmarks to answer this question. And one of them was written by Angelica Lang. Who's heard of Angelica Lang? Definitely. She's a very good speaker. She's very knowledgeable about Java. She wrote a lot of stuff about generics back with Java SE5. And she also wrote a lot of stuff more recently about JDK 8 and streams. And there was a lovely quote in the article which I thought I'd put up here, which is, never trust benchmark figures that you haven't produced yourself. And I think that is absolutely on hitting the nail on the head by saying that. So what we'll also do is just talk very briefly about benchmarking, because benchmarking is one of those things where you look at it and you go, okay, so this is designed to try and figure out what gives better performance. And there are problems with this. So writing accurate benchmarks is very difficult. So that's one thing, especially so for Java code. Java code is notoriously difficult to benchmark because of the JVM. It's not like you're taking a piece of compiled code and just running it, and you can run it repeatedly and then measure the differences based on certain things. The JVM introduces very non-deterministic behavior to your application. You can do things like run a particular piece of code, run it a few times in a loop, and because it doesn't get hit by the JIT compiler, doesn't get compiled, you will see very different results in the short run to one which is much longer, where the JIT compiler does kick in, you do get the advantage of the native code, and things will change dramatically. Similarly, garbage collection pauses can massively skew the results of what you're seeing, unless of course you use Zing, where we've eliminated the problem of garbage collection pauses. So if you're using other JVMs, then garbage collection introduces non-deterministic behavior, and you can really skew the results you get from your benchmark. The other thing about benchmarks is you can often have completely unrepresentative code. If you don't write your benchmark well, you can write a piece of code and you can think, okay, so I'm going to write this code, do it in a loop, and then I'll do something else after it, and I'll measure how long it takes to do this particular piece of code. The compiler comes along and looks at the code and says, well, okay, so you've done all this stuff in the loop, but then you haven't actually used the values that you generated outside of the loop. So we don't actually need to compile any of that because it's not actually being used. So it eliminates all of your code. So you think you're actually benchmarking the piece of code, and you're actually benchmarking none of code because the compiler's eliminated it. JMH is a very good thing to use if you're writing benchmarks. So this is the Java Micro Benchmark Harness, which has been created by Oracle, and does solve a lot of the issues in terms of setting up benchmarks, enabling them to run for a certain number of times, getting them to warm up so you do get the JIT compiler involved and things like that. Right, so the other article that was written about benchmarking of streams versus explicit loops, they created a number of different benchmarks and they ran them and they produced some results. So let's have a look at their graph of results. This is what they came up with. So they said, okay, we'll look at imperative style and we'll look at 3 different ways of doing that. First of those is using a standard old-fashioned for loop, where we'll use explicit values for our indices and we'll go through the for loop. And we'll also try a for each loop, which is clearly the newer syntax. And we'll also try an explicit iterator, because we're working with a collection in this case. And what they found with that was that the iterator and the for each loop came out exactly the same. which is not altogether surprising because if you look at the way that the for each loop is implemented, it actually uses an explicit iterator. So they're both the same in what they actually do. So they came up with the situation here where they found that the iterator, the for each loop, was the fastest way of doing things. The old-fashioned for loop was nearly twice as slow, or 50% slower. And then they looked at the functional style, and they they did some things that were a little bit confusing to start with, because they had one benchmark that they called stream, they had another benchmark they called lambda, and then another benchmark they called parallel stream, which is confusing because you think to yourself, well, hang on, how do you use a stream how do you use a lambda without a stream? Well, okay, you can kind of do that, but what they effectively were saying was that in the case of the stream and the parallel stream, they were using a reduction with a method reference. In the case of the lambda, they were using a reduction, but with an explicit lambda expression. And then the for each lambda was where they used the iterable interface on the collection and said just use that with a lambda expression. And they got these results which showed that in all these cases they were significantly worse than the explicit loop. And it made for great headlines because they said, look, stream's 5 times worse than using an explicit loop. And people got very upset about that. And fortunately, a lot of people looked at this and they said, well, hang on, there's a number of flaws in what you're actually doing with your benchmark. So let's have a look at what they did. First problem they had was, this is a very, well, in my mind, this is a very unrealistic and very narrow focus. What they did was they took a list of random integers and then they tried to find the maximum value in that list. So, yeah, okay, that's certainly something you can do with a stream and you can do it with a loop. But I don't think it's very realistic in terms of what people really do with streams. I mean, I've certainly written quite a lot of stream code, and yeah, occasionally I do something where I'm just finding maximum value. But most of the time I'm using the more common kind of thing, which is, filter, map, reduce, and doing various things with that, sorting, all sorts of more complex operations. So this was a very narrow, very simple example. I think that what they should have done is to really expand it and try several different scenarios and see how those worked in comparison. The next thing they did was they made the list that they were using and they marked it volatile. And you look at that and you go, why? What possible value is there in making that volatile? Now, volatile, as we know, simply means that all the threads that are accessing that variable are going to see the same value of that, so that anything that gets changed gets written through so that all the threads see the same value. Well, they only have one list in this particular piece of code, and that list is set up. And, even they could try and argue, well, okay, maybe it's the values that were in the list, but by marking the list as volatile, it's only the reference to the list which is guaranteed to be written through, not the values in the list. So it really didn't make any sense to have that marked as volatile. They didn't use map to int in their string. So I'll come back and talk about that in a little bit when we talk more about some of the things about how to make streams perform better. They also used integer max. Now, they can be forgiven for using this because, as some people pointed out, there are some boxing and unboxing issues that affect this. And so they would actually be better off in terms of looking at the performance of a stream versus an explicit loop of simply using an if statement which said if A is greater than B, return give A, otherwise B. And then the last thing was they also used a redundant helper method because they got a little bit confused when they wanted to use the iterable interface and for each method because they wanted to modify state through the Lambda expression. And because Lambda expressions are part of Java, Java implements closures over variables rather than closures over values. Closures over values rather than closures over variables. Then they couldn't do that. So they had to have a helper function to call another method to actually make the change in state work, which kind of showed a rather poor understanding of functional programming from my point of view. So they made a lot of changes to their code, and they came up with some new benchmarks, which looked like this. So now, they said, okay, well, the for each loop and the iterator were exactly the same as they were before. They didn't change anything there. Stream suddenly came right down to almost the same performance as the for each loop and the iterator. For each lambda was a little bit slower, so that was using the iterable interface rather than the stream. Lambda, strangely, was a lot slower. I still haven't quite figured out why that one is so significantly different to the rest. Yeah, I mean, surely you get a little bit of improvement by using method reference rather than explicit lambda, but I wouldn't expect to see that big a difference. And at the end, they also improved the for loop, and the parallel stream came out as the best. What can we tell from this? What can we take away from this as a way of interpreting these benchmarks to try and decide whether we should use an explicit loop or whether we should use streams? I think we can safely say that these benchmarks are not much help. They don't really give us any idea of whether we should use an explicit for loop or a stream for general cases. Much safer, if you are very, very concerned about performance, is to measure the effects on your code and with a realistic workload on that. So you should be doing benchmarks using what you're trying to do rather than simply saying, oh, this is a random thing that somebody's picked, and that shows that in certain situations you get better performance with one thing rather than the other. The other thing that's also really important about this is to understand, is performance absolutely critical to you? Now, are you interested in getting that absolute last sort of few microseconds, milliseconds out of your code at the expense of readability, at the expense of a high level of abstraction? Because streams is not just about performance, it's about making your code easy to read, easy to understand, and less error prone. And like I said, that's a whole separate talk on how streams work from the point of view of developing code. Right, so let's talk a bit about tips for better performing streams. What can we do to improve things? Right, so one of the things that I've done in the past is run a number of hands-on labs where we've given people exercises to do and we've got them to solve them using lambdas and streams as a way of learning about how to use these things. And one of the things that we gave people was a simple task, which is we give you a list of words, give you a file with strings in it, and we want you to find the longest line in a file. Okay. And we'll use a buffered reader as an input, so you can get the stream of lines from the buffered reader. What you do with your stream can greatly affect performance, as we will see. Now here is what I describe as my naive stream solution, because this was my first attempt at doing this a long time ago when I first started using strings. So I said, okay, let's take our lines, and what we want to do is we want to get the longest line, so we'll sort all the lines in the file by length. So we'll use a comparator as our Lambda expression here, and we'll sort based on length, so that the longest line is the first in our sorted list. Then we'll pass that into find first. Whatever is the first line that we take from that stream is going to be the longest line, or one of the longest lines in that file. And because that returns an optional, we do a get to extract value from that. So that works. Job done. Everything's fine. Unfortunately, not so much, because of course, if you have a really big file, in fact, you really need to have a very big file, you're going to take a very long time to do, because in addition to having to read through all of the lines in that file, you've then got to sort them all and then pick the first one from the top of that list. So it's going to take a lot of time and a lot of resources. So that's not going to be the best way to do it. It works, it is an approach, it is a solution, but not the best one from a performance point of view. So what we could do is we could use a reduction. We know that we can do things like filter, map, reduce, so let's just do a reduce. So we take our lines, and then what we want to do is we want to reduce the lines in that file to a single line, which is the longest one. And if you look at how reduce works, what we're defining here is an accumulator, and the accumulator takes two values here to implement a binary operator. So x is the partial result that we have so far, y is the next element in our stream, and then we just generate a new partial result from that and pass it on until we get through the whole string. So all we're doing here is simply returning either x or y depending on which is the longest. So as it goes through, it's just going to keep track of the longest one until we get to the end. So that will work. So that's a better solution because it's only reading through the lines once. Great. But there's also a better way of doing that. Simplest stream solution is to use the max terminal operation. So in that case, we can use the one which takes a comparator as a parameter, and we can say, take our lines, pass it to the max. We'll use a comparator which is predefined, compare int based on the length of the string. So that will go through and compare the string's length, pretty much do the same thing as before in terms of our reduction, and give us the same result. So there are different ways of doing the same thing, but from a performance point of view, different results that we'll get. Okay, let's look at another simple example of how we can change things in terms of how the string works. This was the idea that we wanted to concatenate the first letter from each word in a list. And if the input was Alpha, Bravo, Charlie, Delta, Echo, Foxtrot, then the result would be A, B, C, D, E, F. So that's what we're looking for. And the solution that we gave to do this, streams are no exception to the program, the solution we gave was to use a string builder and then use the iterable interface on the list and simply say for each, take the string that we get from the list and append to our string builder the character at 0 and then extract from that the result, which is the string, and it gives us the result. So that's a nice and simple way, and it works because we're using a string builder. It's effective from the point of view of strings. One of the times I did this, we got talking about this with the people who were doing the exercises, and somebody said, well, can you do it with reduction? And I said, well, yes, you can. You do it like this. So you can say input stream map. In this case, we have to use substring 0.1 because we need a string as output rather than a character. So we'll do substring 0.1, and then we'll reduce that. And in this case, we'll use the reduce method where we pass it an initial value, which is an empty string, and then we pass it the accumulator, which is simply A and B, and we just concatenate A and B. So that's all well and good, but of course that's far less efficient than the first example because now we're doing lots of string concatenation. Strings are immutable, so we have to create new string objects each time, so there's a lot of overhead in terms of invisible objects that we're creating under the covers. So somebody said, well, can't we do a reduction but using a string builder? So I thought, okay, yeah, let's do that. That'll be fun. So I came up with this. So I said, okay, string builder, map to substring, and then we'll reduce A and B, and we'll append B to the string builder, and we'll return an empty string. Because remember, we're only updating the string builder, so we don't really care about what's actually happening in terms of the reduction itself and the partial result. And we extract the result. So this failed. So anybody spot what I did deliberately wrong here? Okay, so nobody's going to spot it, so I'll give the answer. So the problem is, what I actually got back was B, C, D, E, F. The reason you get B, C, D, E, F back is because in the reduce, when you use the accumulator there, A represents the partial result so far, B represents the next element in the stream. When you start processing the stream, you have no partial result. So the partial result is actually the first element in the stream. So the first element is called, you get the first element and the second element passed as parameters. And then the second time, obviously, you get like the next element and so on. So effectively what was happening was it was missing the first element. So I thought, okay, I can fix this. I can write Java code. So I did. I came up with this. It's getting rather like iffy now. So yes, so we said if the length of A is 1, so the first time it gets passed at a string, it's the length 1, so that's the first character from the first element in the string. Append A, then append B, and because we return an empty string each time, the next partial result is going to be an empty string, so we won't append A each time. So that will actually solve the problem, and it will work. I'm not saying it's the best solution, I'm just saying it's a solution. And of course, then I actually thought about this, and I thought, well, you don't actually need the if statement there, because what we could do is we could simply eliminate that and say append A and append B over time, because we're returning an empty string. So the second time and subsequent times, you'd simply be appending an empty string to the string buffer. Now, I'm not sure, I haven't bothered to benchmark, I really didn't bother to benchmark this, to see whether keeping the if statement there is more efficient than removing it. So which takes longer, the comparison based on the length or appending an empty string to the string buffer, string builder. Right, but then there's another way we could do it. So we can say, okay, rather than doing it that way, let's use our collect method, which makes more sense. So a collect method is a mutable reduction on the input string. So now we can say, okay, take this and collect it, but what do we put in terms of the collect? So we can create a collector. So we'll do it like this. We do it the longhand way. So you can use collector.off, and then we'll say that in the case of a collector, there are certain things we need to specify. So we need to specify firstly the supplier, which is what we're going to put the results into. So that's a string builder new. We then have an accumulator, which is what we do with each new value we want to put into this collection. So we're going to append that. We then have a combiner, which is actually the same as the accumulator. And the reason you have a combiner and an accumulator is because if you have a parallel stream, this can be broken up into multiple operations. So that the combiner is what is used to combine the results from each of the different threads. So the combiner does the same thing as the accumulator. And then the finisher is what we do to get the result out of that, which clearly we want to get the string from there, so we do toString. And then there's also some characteristics which we don't need to bother with because that's to do with like mutable collections and stuff like that. Of course, there is a far simpler way of doing that, which is just to say use the collector's joining method, which if you look at joining actually does exactly what I did with collectors.off. So it's exactly the same in terms of the collector. So that really was just, what I wanted to do there was demonstrate that there are many ways that you can approach the same problem using strings, some of which are going to be better performing than others. How you determine which is the best performing one is really down to measuring it with your code and your data set to find out which makes the most sense. A couple of other things that are worth bearing in mind. Multi-sort. This is the suboptimal way of doing it. So let's say we've got some patient records and we want to sort them based on the patient name. Then where the patient name is the same, we want to sort based on physician, and where the physician is the same, we then want to sort on medication. So we could do that by doing filter, sort, sorted, 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 and then collect to list. But what we're doing there is effectively 3 sorts, which is very efficient. There's a much better way of doing that with the Streams API, because you can do sorted comparing patient get name, and then you can use then comparing to chain together where the sort happens. So anything where the patient name is the same, it will then compare based on position, it will then compare based on medication. So that's a better way of doing it if you want to do multiple levels of sorting. Coming back to the benchmark earlier on and talking about boxing and unboxing. So what we're doing here is we're saying, okay, get a list of integers and we want to get the maximum value from that. In this case, what we're doing is we're saying take the list, string from the list, and then do max using math_max. We use integer max, but in this case we're using math_max. Lots of unboxing going on there, because what we have is a stream of integer objects. Integer objects then have to be unboxed, processed by the max method, and we have to determine max value from that. Better way of doing that is to use map_to_int, where we convert from a stream of objects into a stream of primitive values. So in this case, we're going to say take that stream of integers, convert it into a stream of ints by getting the int value from the integers, and then passing that to max. Now, you might think, well, hang on, isn't that really just doing the same thing? Because in effect, map to int is unboxing the values from the string of integers. You might think that, but if you look at the actual performance, the way that works, you will get better results by doing map to int, and then what's happening underneath in terms of the stream is more efficient. Right, parallel streams. When streams came out, people got very excited, and they said, streams everywhere. Let's use streams for everything. And then they got even more excited because you could use parallel streams. So they said, right, let's use parallel streams everywhere, because parallel streams will make things run faster. We can get our results quicker because we can use parallel streams. Right, let's have a little bit of a look at parallel and serial streams. So the first thing is, the great thing about streams is it's very simple syntactically to change from doing everything serially to doing things in parallel. So what we can do is we can say, okay, I've got a list and I'm going to get that as a stream, which means that I'm getting a sequential stream that we're going to process. If I want to do that in parallel, all I have to do is change that to be parallel stream rather than stream. And that will give me a parallel stream. Great. But I can also use serial or parallel to change midstream. So I can say, right, so what I'm going to do is I'm going to create myself a parallel stream, then I'm going to filter that in parallel, then I'm going to change it to serial. I'm going to do my map to int serially for some bizarre reason which I can't explain. And then I'm going to change it back to parallel and do the sum. No. Yes, you can put the code like that. You can make yourself think that that's what's going to happen, but it's not. Because the thing is that when you create a stream, it actually coalesces all the operations of that stream into a single set of operations. So what you'll find is that the whole stream is either processed sequentially or it's processed in parallel. And you can put as many calls to serial or parallel in that stream as you like, but it will be the last one that wins. So in this case, we had parallel as the last call, so everything in that particular stream will be done in parallel. Regardless of the fact that we put serial above it, we'll do it in parallel. To improve things, obviously operations should be stateless and independent. Very important if you're going to do things in parallel. Right, how does this parallel stream work underneath? Well, parallel stream uses the ForkJoin framework. ForkJoin framework was introduced in Java SE 7, and what that allows you to do is take a big task, which can be broken down into subtasks, and that can happen recursively until we get to a small enough task that can be executed in a single thread. Framework will do all of the hard work for you in terms of creating a pool of threads. It will allocate jobs to the queues. It will handle different things in terms of getting the queues to finish, doing work stealing, and things like that, and then give you the result. When the JVM starts up, it creates the common ForkJoinPool. This is a ForkJoinPool that is available for you to use when you want to use the ForkJoin framework. And by default, the number of threads will be equal to the number of CPUs reported by operating system. This in itself is an interesting little piece of information because I've seen several people talk about this subject in presentations at conferences, and some people say you actually get twice as many threads as you have reported processors from there. Some people say it's as many threads as reported CPUs plus one. No, I went and I checked, I dug into the source code, and I found out that it is definitely the number of CPUs reported by runtime.available processors. Another little interesting snippet of information about this is if you're running microservices. So if you use Java in a microservice and you create a container for your microservice to run in, and you use a C group and you say, I only want this C group to have, let's say, 2 cores available to it, whereas I have 8 cores in my machine. How many threads do you think you're going to get in the common ForkJoinPool? Are you going to get 2 or are you going to get 8? Yes, you're going to get 8 because this call is not C group aware. So even though the C group is restricted to only using 2 cores, what you'll get back from available processors is what the machine has, not what the container has. So that's something to bear in mind when using microservices. Right, you can change it manually. So there's this very easy to remember command line option, -d java.youtube.concurrent.forkjoinpool.com.parallelism, and you can set that to be whatever you want it to be. Right, so let's take an example of that. Let's set our parallelism to be 4. So we're going to use 4 threads for our common fork join pool. Let's write some code. So we'll create a parallel stream, and then we're going to use peek to look at what's actually going on with our parallel stream. And we will add the name of the current thread to the concurrent set that we've got here. We're being a bit cheeky in terms of modifying state within our functional code, but we'll ignore that. And then we do some filtering, mapping, and whatever. Great. Then we're going to print out how many threads we've got. Now, I've said it to be 4. So, hands up, who thinks the answer to this is 4? Yes, because obviously I wouldn't ask this question if the answer was going to be 4, would I? Who thinks it's less than 4? Who thinks it's more than 4? And so most people don't have an opinion on this. Okay, so the answer is 5. So you've set the parallelism to be 4, and we get 5 worker threads. Right, so what we'll do this time is we'll do exactly the same thing, but rather than printing out how many we've got, let's print out the names of the threads. See what we get. And what we end up with is the 4 workers that we expect to get for our parallelism, but we also get main as well. Ah, interesting. Right, so what's going on here? Well, what happens is that the invoking thread is also used as a worker, because the way that the parallel stream implements this is it says, well, parallel stream is invoking the fork join framework synchronously, which means it's blocking until the work is done. So that thread is just sitting there doing nothing. So why don't we use that one and bring it into the pool so we can get the parallel job to happen more quickly? Well, yeah, see, I'm not totally convinced by that, because if you set the number of threads to be 4, because you think, right, I've got 4 cores on my processor, I want to run 4 threads simultaneously, and then suddenly it's got 5 threads, you're going to get context switching and all sorts of stuff, which might not actually improve performance. So other things to be aware of when doing this is beware I/O blocking actions inside stream operations, because obviously if you're doing I/O operations, that's going to delay things because it will block that thread, and so you will get significant slowdown in what's happening. Make sure all your stream data is in memory, because again, you don't want to be going out and actually accessing stuff off disk to get your data. Do not nest parallel streams, because if you nest parallel streams, even though you won't have a problem from the point of view of corrupted data, you will be using the common fork join pool for all of those parallel streams, which means you're trying to contend for a limited set of threads to do all of the things that you're trying to do. Often that will perform worse than if you have serial streams nested inside a parallel stream. So that's just something to be aware of. And also ensure that the reduction accumulator is associative, so it doesn't matter which order you do things in, that will help with the parallel operations. Another thing to be aware of with parallel streams is that if you don't care about the order of things, then add an unordered call, because this will actually help. Certainly in terms of things like distinct and limit, those will work better, but even things like if you're doing a simple filter and collect, if you set the parallel stream and you say be unordered, then it won't do as much work underneath, and you actually get better results in terms of the performance of that stream over one where you don't put unordered in there. There is what I call my custom pool hack. This is if you really do want to run nested parallel streams, then you can do it this way. So you create your own fork join pool, and then you submit the parallel stream operation to the custom pool, and then the parallel stream will use your pool rather than the common fork join pool. So you can create more threads and have the work take place in a different set of threads, so you don't get the problems of nested parallel streams bumping into each other. And in that case, you will get a work account of 4. So you will actually be correct where you've got 4 threads and you really are getting 4 threads being used. So, is a parallel stream faster? Another common question is like, well, if I do it parallel, surely it's going to happen faster. No, not guaranteed. What is guaranteed is that a parallel stream will involve more work than a sequential stream, because a parallel stream has to set up the fork join framework. So there's the whole idea of having to create not necessarily create the pool of threads, but it has to set up the queues, it has to allocate the jobs to the queues, do all of that work, set up the framework, and make it do its job. That is overhead beyond what you're getting with a sequential stream. You might, if you're lucky, complete more quickly. How do you know? Well, it depends on several factors. Firstly, how many elements are there in your stream? And that's something that's fairly easy to measure, because you can count it. Second thing is, how long does each element take to process? Now that's a bit harder to do. You have to do some benchmarking on that. And basically, the higher the value of n times t, the better your parallel stream is going to work from an efficiency point of view. That doesn't mean that n and t have to be big. One of them has to be big, but it doesn't have to be both of them. If you had, let's say, 8 elements in your stream, and each element took 1 second to process, then obviously if you run them sequentially, it's going to take 8 seconds for everything to work. If you have 8 cores available and you can run them truly in parallel, you could potentially get them to finish in 1 second. So it doesn't have to be that n is big or t is big, it just has to be both of them together to give you a big number. The type of operation will also impact how well a parallel stream can work. So if you use things like map and filter, those are very good. They decompose completely into parallel operations. You can do as many mapping and filtering things independently of one another as you want. Things like sort, things like distinct, because they rely on data that's in the set and there's a dependency between the data, those will not decompose so well into parallel operations. So if you're doing things like mapping and filtering, great. If you're doing things like sorting, distinct, then you will get not quite as good performance out of your parallel. One other thing I'll just talk about is something that's coming in JDK 9, which is support for parallel support for lines in files. So what this is going to do is it's going to take a file, and whereas before, if you wanted to try and process that in parallel, you weren't going to get anywhere, because of course the file was read sequentially. Even if you try and process it in parallel, it's just not going to work. What happens now is that the file gets mapped into memory, and then the streams code will look at that file and can divide it up based on line breaks and try and divide it into roughly even chunks, and then divide it approximately in half as many times as you want. What that gives you in terms of performance is if you're using buffered reader.lines, is in blue is sequential and green is parallel. So if you try and use parallel on an existing file using buffered reader, you actually get worse performance. If you use the new Files.lines, then you can see here it's probably got a quad-core processor there, and you're getting a speed up of about roughly a quarter or 4 times. Right, summary. Lambdas and streams are very powerful, wonderful. Tuning for performance is the same as other areas of Java. So the right code can run fast, the wrong code can run slowly. So it's just as easy to make mistakes with streams and lambdas as it is with other parts of Java. Parallel streams may improve the performance of your application, depending on the size of the data you've got and the complexity of the element processing. I'll leave you with the quote from Knuth, who said, "Premature optimization is the root of all evil." And then just one shameless plug for on the part of Azul in terms of our products. So we have Zing and we have Zulu. So Zing is our high-performance, low-latency commercial JVM, where we have solved the problem of garbage collection pauses. They just go away. And also try that for free. So if you're interested in looking at how that will help your application, you can go to our Zing free trial. And then we also have Zulu, which is a pure build of OpenJDK source code. And we guarantee that it's fully conformant with Java SE. It can be called Java. There's no problems on that. And it has no licensing restrictions. So it is available for free. You can download it from our website. And if you're interested in commercial support, we will very happily talk to you about that. So that is that. So if anybody's got any questions, we're very happy to take them.
Is there like not really a framework, but more importantly, kind of directions around integration of when streams originally came out, right? People got excited because you could, in theory, make that distributed, right? And you would have the same syntactic expression language, right? But the stream itself is basically an integrator, right? And the concept of an integrator, if you may, is basically it could be on the same machine, it could be coming in from different machines, right? So what are your thoughts on that?
Well, it's not really an iterator, no.
It's the logical sense of like basically you're encapsulating, if you may,
yes,
the concept of where the data is, right?
Yes.
So you're basically making, if you may, operations that can be applied on streams of data, and stream by means of not a JVM stream, but streams in general, basically a set of tuples that are coming in.
Right.
So what are your thoughts on like that being distributed in the future? Because there's Spark, but it doesn't really conform very well to the whole streaming framework, and if you try to use it with Lambda, there's a whole lot of mess that you end up generating.
I'm not really sure how to answer that. I mean, streams work very well in the way that they've been designed. And I mean, they are designed to give you an abstraction over how you can process a collection of data, where you're not necessarily, because you're not really thinking of it as an iterator. That's actually the wrong way to think about it, because you're really thinking about how to process all the elements in that collection, not as a sort of sequence of elements, but how you apply a set of operations to it. Because that's the whole idea, is you want to move away from thinking of it as one element after another, to just simply what are the operations that you want to apply to that whole set of data, and then let the stream underneath deal with the complexity of how that actually happens. And that's why changing from serial to parallel becomes very, very easy, because you're not worried about, you don't have a contract in terms of the order that things happen. How that relates to things like Spark, which you mentioned, I think that will improve over time. You know, as people adopt more of the JDK 8 syntax into some of these frameworks and libraries, I think it will get easier over time. Yeah, I think that's probably the easiest solution or answer I can give to that.
So you mentioned Lambdas, the JVM, we can look at them if they're not capturing, if static methods, if they are capturing, but of class variables, they can make them methods on variables. What if you have method or Lambdas that are identical and use them multiple times for whatever reason? Do you have any preference, or is there any difference? Is the JVM able to reduce that to the same method as opposed to maybe creating a single static instance?
Yeah. No. If you're using the same Lambda expression, so if its signature is exactly the same, then the JVM will be smart enough to realize that you only need one static method, because it'll be the same signature. So you don't need to replicate it however many times.
But you're capturing is part of that.
Well, yeah, it's a factor, but still, if the bytecode is identical, the JVM should be able to not create two methods, should be able to know.
Yes. Yeah. If they're identical, then there should be no issue.
Yeah, if you capture a whole state, of course that's going to change.
Are those synthetic classes generated by Lambda server unloaded by JVM. Or do you have any idea about that?
Synthetic classes.
So I guess by Lambda, synthetic classes can be generated by on the fly, right?
No, because that's the whole point. We're not with Lambdas. You're not generating a class.
Unimplemented does.
Was
And
that-
they do get garbage.
Yeah. Okay, I defer to Doug on this one. He knows far more about the way it works in terms.
Yeah, you want to know the details? We'll talk. This will be fun. Where it gets really messy is when you try and debug a stack with them, because the symbols show up.
Yes. Okay. Pretty much bang on 8 o'clock. There you go. Well, thank you very much.